So, what if I told you that when you buy a brand new, super powerful 128-core computer, the operating system running it is based on a design from the 1970s? Well, that's pretty much the reality we're living in. Our processors are getting exponentially more powerful, but the core software we all depend on is, kind of stuck in the past. Today, we're going to dig into why that old design is finally hitting a wall and what the incredible new blueprint for a truly modern OS actually looks like.
Right, so you've got this absolute marvel of silicon, a 128-core CPU. You'd think, pretty logically, that as you add more cores, your performance just skyrockets. But with operating systems like Linux or Windows, something really, really weird happens. After a certain point, adding more cores actually makes things slower. How is that even possible? Well, the answer is a deep, fundamental flaw in the architecture at the very heart of the OS, the kernel.
And the villain in our story today? It's the monolithic kernel. For decades, this has been the go-to design. One enormous, super complex program that tries to handle absolutely everything. And hey, it was brilliant for its time. But on today's hardware, with all this massive parallelism, it is slammed headfirst into what you could call a monolithic wall. To get past it, we have to fundamentally rethink the whole idea of what an operating system should be.
So this slide really breaks down that wall into a few specific performance-killing traffic jams. Just imagine 128 cores all trying to update the very same piece of data in the kernel. What happens? They have to get in line, waiting for a digital bouncer called a lock. That's lock contention. While they're just sitting there waiting, that data is getting bounced back and forth between all their local caches, which is just a huge waste. And every single time a program needs to talk to the kernel, a critical part of the CPU's short-term memory, the TLB, which is kind of like the CPU's address book, has to be totally erased. It's a system that was designed for one-on-one conversations, and now it's trying to referee a shouting match in a packed stadium.
Okay, so how do we possibly fix this? Well, the very first step is to completely change how we enforce security. Instead of relying on these slow, complicated software walls, the new idea is to push that job down into the silicon itself. We're essentially moving from software rules to something more like the laws of physics, enforced right on the chip at full speed.
And that leads us to our first huge concept, the Single Address Space Operating System, or SASOS. See, in a normal OS, every single application lives in its own private, walled-off memory bubble. And switching between those bubbles, it's incredibly slow and expensive. A SASOS, on the other hand, puts everything, the kernel, the drivers, all the apps, into one gigantic shared address space. And why does that matter? It's massive. It means we can completely eliminate those costly switches and the performance-destroying TLB flushes that go with them.
But wait a second. If everything's in the same shared space, isn't that a total security nightmare? Normally, yes, but not when you have hardware capabilities. The best way to think of a capability, like the ones from the Sherry project, is as an unforgeable digital keycard. When a program gets a pointer to some memory, it comes with this keycard attached, and the CPU itself checks that keycard on every single access. It says exactly where you can go and what you can do, read, write, or execute. It means even if a hacker finds a bug, they're trapped. They can't use it to wander around in memory where they don't belong.
So let's compare these side by side. The old way uses a memory management unit, the MMU. It manages memory in these big, chunky, inefficient pages. It's slow and it's coarse. The new way uses capabilities, and they're checked at lightning speed right inside the CPU pipeline. A call from an app to a driver just becomes a simple function call, not some big, heavy system call. The result? This is the holy grail of performance, zero TLB flushes. The performance tax we've always paid for security, it just disappears.
So, with isolation now solved by the hardware itself, we can go after the next big bottleneck, the centralized kernel. And our second building block here is to stop thinking about the kernel as one big program and start thinking about the CPU as a distributed network.
This is the key insight from some really pioneering research, like the barrelfish system. In a multi-kernel, you don't have one OS trying to manage 128 cores. No, you have 128 tiny, independent OS instances, one running on each core. They don't share data, they don't share locks. Instead, they behave like they're separate computers on a network, and they communicate only by sending messages back and forth.
So how do they talk to each other? Well, we're not talking slow network packets. It's more like a super high-speed circular conveyor belt that's built right into the chip connecting the cores. One core puts a message on the belt, the other one picks it up instantly. It's lockless, which means no waiting in line. And it's zero copy, so no redundant data shuffling. You're basically using the CPU's own internal highway system to make messaging between cores almost as fast as a local memory access.
Okay, so we've got fast communication, we've got hardware security, we're almost there. But there is one last, really subtle ghost-in-the-machine kind of problem. In a system where there are billions of these shared pointers flying around, how do you safely delete anything?
I mean, here's the challenge, right? You tell the system to free a block of memory, but what if some other core, way over on the other side of the chip, is still holding a valid hardware capability, a key card, to that exact same spot? If you reallocate that memory to something new, that other core could use its old key card to come in and corrupt all the new data. And the simple solution, like just pausing the whole system to find all the bad pointers, well, that would absolutely destroy performance. Thankfully, modern systems like CherryVoke have a way more elegant solution. Here's how it works. First, when memory is freed, it's put into quarantine. It's marked as unusable, but it's not actually reallocated yet. Then, using this very clever data structure called a shadow map, the system can quickly find all the dangling pointers. After that, a background process just sweeps through memory and invalidates all those old keycards. And only then, once every last reference is gone, is the memory actually reclaimed and put back into use. It all happens asynchronously, so you avoid any of those big system-wide pauses.
So let's just put all the pieces together. We have hardware capabilities for fast, fine-grained security. We have a distributed multi-kernel for lock-free parallel computing, and we have deterministic revocation for safe memory management. You see, this isn't just a few small tweaks, it's a completely new blueprint for an operating system, designed from the ground up for the many-core world we live in now.
There's this quote from the research that just perfectly captures this whole shift. It says, "The microkernel ceases to be an intermediary and becomes a pure traffic controller." I love that. The OS is no longer this meddling gatekeeper that's involved in every single transaction. It's a traffic controller. Its only job is to route messages, manage the capabilities, and then just get out of the way and let applications talk directly to each other and the hardware at full speed.
Let's put the two architectures head-to-head. The monolithic kernel, it hits a hard scalability wall. The multi-kernel scales pretty much linearly. The cost for programs to talk to each other, it goes from being super high to near zero. Security, we go from these big, coarse-grained fences to fine-grained, hardware-enforced locks. And the whole design model shifts from this centralized, contention-heavy model to a distributed, message-passing one. It is a fundamental win on every single metric that matters for modern hardware.
Now, I know all of this might sound like it's years and years away from being practical, but the transition is already happening. Let's take a look at the real-world progress that's being made to bring this architecture out of academic papers and into the devices we actually use.
No, this is not science fiction. Back in 2022, ARM shipped the Morello board. That's a real-world prototype processor with Sherry hardware built in. Microsoft is already exploring this stuff for secure Internet of Things devices. There's a mature open-source OS called Sherry BSD that you can run on this hardware today. And the whole open standard RISC-V movement is working to make capabilities a standard extension. Really, the final piece of the puzzle is just getting our compilers and software tools up to speed to really leverage all this new power.
And that leaves us with this one last really exciting question. For decades, our software has been built around the limitations of these old monolithic operating systems. So what happens when those limitations are finally gone? When we have operating systems that can truly scale to hundreds, maybe even thousands of cores, what entirely new kinds of software are going to become possible? It's a pretty exciting future to think about. Thanks for watching.